My name is Teresia and I'll be taking you through integration by partial fractions. So we are going to start with decomposition into partial fractions. If P of x over Q of x is an algebraic fraction where the degree of P of x is lower than the degree of Q of x and Q of x is fully factored into linear factors, then we can decompose P of x over Q of x into partial fractions. For each unique linear factor of Q of x, say x minus a, we have a single algebraic fraction in the decomposition of the form of a over x minus a. If Q of x has repeated factors, say x minus b is repeated twice, then we have two algebraic fractions in the decomposition of the form of b1 over x minus b and b2 over x minus b squared for each power of the repeated root. To decompose algebraic expressions into partial fractions, we should consider the type of the denominator. For every type of the denominator, we are going to form partial fractions of different forms. 1. If the denominator has linear factors expression of the form of f of x over x plus a into x minus b into x plus c, we are going to have partial fractions of the form of a over x plus a plus b over x minus b plus c over x plus c. If the denominator is a repeated linear factors expression of the form of f of x over x plus a cubed, we are going to have partial fractions of the form of a over x plus a plus b over x plus a squared plus c over x plus a cubed. And finally, if the denominator is a quadratic factors expression of the form of f of x over ax squared plus bx plus c into x plus d, we are going to have partial fractions of the form of ax plus b over ax squared plus bx plus c over x plus d. We are going to have our first example whereby we are going to find the integral of 11 minus 3x over x squared plus 2x minus 3 with respect to x. For us to integrate this algebraic expression, we are going to start by decomposing it, whereby we are going to factorize our denominator, that is x squared plus 2x minus 3, whereby we can use the sum and product rule, and we are going to get two linear factors, that is x plus 3 into x minus 1. So we are going to rewrite our fraction as 11 minus 3x over x plus 3 into x minus 1. So to express this algebraic fraction into partial fractions, we have seen previously that for a denominator with linear factors expression, we are going to form partial fractions of this form, that is a over x plus 3 plus b over x minus 1. When we add the partial fractions, we are going to have a into x minus 1 plus b into x plus 3 over x plus 3 into x minus 1. When we look at our denominator, they are equal, so we can equate our numerators. We are going to have 11 minus 3x is equals to a into x minus 1 plus b into x plus 3. We want to find the values of a and b, so we are going to let our x to be equal to 1. When we substitute the value of x in our equation, we are going to have 11 minus 3 is equals to a into 0 plus b into 4. Whereby we are going to, when we solve, we'll get the value of b as 2. To find the value of a, we are going to let our x to be negative 3. And when we substitute the value of x in our equation, we are going to have 11 minus 3 into negative 3 is equals to a into negative 4 plus b into 0. And by solving this equation, we'll have our a as equal to negative 5. So we are going to rewrite this fraction as 11 minus 3x over x squared plus 2x minus 3 is equals to 2 over x minus 1 minus 5 over x plus 3. To integrate 11 minus 3x over x squared plus 2x minus 3 with respect to x is the same as integrating these partial fractions separately. So we are going to integrate the partial fractions separately, whereby we will start by taking out the constant outside the integral sign, and we are going to have 2, the integral of 1 over x minus 1 with respect to x, minus 5, the integral of 1 over x plus 3 with respect to x. So for us to integrate 1 over x minus 1 and 1 over x plus 3, we are going to use the substitution method, whereby we are going to let our u1 to be equals to x minus 1, and by differentiating this equation, we are going to have du1 over dx is equals to 1, implying that dx is equals to du1. We are also going to let our u2 to be equal to x plus 3. When we differentiate this equation, we are going to have du2 over dx is equals to 1, implying that our dx is equals to du2. We are going to replace our x minus 1 with u1 and our x plus 3 with u2. So when we integrate 1 over u1, we are going to have natural logarithm of absolute value of u1. And when we integrate 1 over u2, we are going to have natural logarithm of absolute values of u2. So when we rewrite this, we are going to have 2 natural logarithm of absolute values of u1 minus 5 natural logarithm of absolute values of u2 plus c, that is the integral constant. So we are going to replace our u1 with x minus 1 and our u2 with x plus 3. So we are going to have 2 natural logarithm of absolute values of x minus 1 minus 5 natural logarithm of absolute values of x plus 3 plus c, the integral constant. So we can rewrite our solution using the laws of logarithm, whereby we are going to have natural logarithm of absolute values of x minus 1 squared over x plus 3 power 5 plus c, the integral constant. This brings us to the end of our session. Thanks for watching.